In this video, we're going to look at the common ion effect and what effect that has on solubility of ionic substances. So we can dissolve ionic compounds in solutions other than water. If we add an ionic compound to an aqueous solution that already contains ions of that compound, that means that less of the ionic compound, the solute, will dissolve. This means that the solubility of the compound will be less than it would be in water or without the common ions present. This makes sense when we relate this to Le Chatelier's principle. Consider the above equation. If we were to mix the above solution with potassium iodide, then we are effectively adding more iodide ions. Since we're increasing the concentration of the iodide ions, the system will shift in order to minimize this disturbance. The equilibrium will therefore shift to the left to create more precipitate, using up those extra iodide ions. So let's compare the solubility of silver iodide in water with the solubility of silver iodide in a potassium iodide solution. Let's start by looking at the solubility of the silver iodide in water. So first of all, let's consider the KSP. So your KSP will be on your data sheet, and the KSP for silver iodide is 8.52 times 10 to the negative 17. Our expression for KSP is the product of our ions. So to represent the solubility of these, we can either sub in the use of X, or often you will see the letter S to mark that we're looking at solubility. So since they're a 1-to-1 ratio, they both have one S, and that means that the KSP is equal to our solubility squared. So remember, our KSP is up here, and that equals S squared. So S is going to be the square root of our KSP value. So therefore, our molar solubility of our silver iodide in water is 9.23 times 10 to the minus 9. Now let's compare what our molar solubility is in a potassium iodide solution of 0.2 molar concentration. So again, we have our KSP for our silver iodide, and again, we're going to let S represent our molar solubility. Now the difference here is, while we've got the same KSP expression, when we go to sub in our S, what we actually have is S for our silver ions, that's as normal. But for our iodide ions, we actually have 0.2 molar already in solution. We already have 0.2 molar iodide ions, and then we have S, or the solubility of from the silver iodide that we're trying to dissolve in the solution. Now, because it already has the iodide ions in there, we actually don't count this. So we actually remove it from this expression for our calculations. The reason for that is the amount of the iodide ions from our silver iodide that are going to dissolve into solution are so minimal, we do not even count them. They're so tiny, such a small amount that we just pretend like they're not even there. And if you were actually to do the whole calculations with it, at the end, the rounding on your calculator will show that it's so small it doesn't even count. So we get rid of that, and that means that for this particular example, the KSP equals 0.2, this 0.2 times S. Now, if you compare the molar solubility in water to the molar solubility in potassium iodide solution, we can see it's as we would have expected. There are more ions being able to be dissolved into the water than there is in the potassium iodide solution because of the common ion effect. Because there are already the iodide ions in solution, we have much less that are able to dissolve into that solution.